I am Mrs.S.Malathy, Head Associate Professor of Chemistry, A.D.M College for Women, Nagapattinam. I am going to discuss about organometallic compounds for 3rd BSc Chemistry students. What are organometallic compounds? The organometallic compounds are those compounds in which central metal atoms are directly bonded with the carbon atoms of the hydrocarbon radical or molecule. The organometallic compounds combine an organic moiety with a metal in a molecule that has direct metal carbon bonds. Example, nickel tetracarbonyl, where nickel is bonded with carbon, forming organometallic compound. Even though the carbon monoxide is not hardly an organic compound, it is bonded with nickel, and undoubtedly the chemist told that it is an organometallic compound. The bonding is ionic or covalent or delocalized between organic groups and a metal atom. Now we will discuss about what are the classification of organometallic compound. On the basis of nature of metal carbon bond, it is of 3 different types: ionic bonded organometallic compounds, covalent bonded organometallic compounds, and multi-centered organometallic compound. Let us see what is ionic bonded organometallic compound. The organometallic compounds of alkaline earth metals, lanthanides and actinides are predominantly form ionic compounds. These are generally colorless compounds, extremely reactive, non-volatile solids and insoluble in organic solvents. Example, triphenyl sodium and cyclopentadienyl, bis-cyclopentadienyl calcium and cesium methanide and cyclopentadienyl sodium. These are the examples for ionic bonded organometallic compounds. The next one, the covalent bonded organometallic compounds. Here there are 2 different types, that is sigma bonded organometallic compounds and pi bonded organometallic compounds. In sigma bonded organometallic compounds, these are the compounds in which carbon atom of the organic ligand is bonded to the metal by a 2-electron 2-centered covalent bond, 2E2C covalent bond, generally formed by most of the elements with values of electronegativity are higher than 1. Example, nickel tetracarbonyl and iron pentacarbonyl. Here only sigma bonds are present between the carbonyl group and the nickel atom, and the carbonyl group and iron atom. These are known as sigma bonded organometallic compounds. Next one, pi bonded organometallic compounds. These are alkene, alkyne or some other carbon group has a system of electron in pi orbitals. Overlap of this pi orbitals with vacant orbitals of the metal atom gives rise to arrangement in which metal atom is bonded to several carbon atom instead of to one. For example, bis-cyclopentadienyl ion. Here 2 phenyl groups or cyclopentadienyl groups are attached to the iron atom. Then next one, Zyzzy salt. Here potassium trichloro bis ethylene platinate is obtained, that is known as Zyzzy salt. These are the examples for pi bonded organometallic compounds. The next one is multi-center bonded organometallic compounds. The compounds in which a loosely bonded electron deficient species exist with a coordination of metal like lithium, beryllium, aluminum, etc. Example, methyl lithium and tetramethyl and tetralithium. These are the examples for multi-center bonded organometallic compound. Then next, classification of ligand based on hapticity. Organic ligands are classified according to number of carbon atoms within a bonding distance of metal atom or the number of carbon atoms through which an organic ligand is attached to the central metal atom is known as hapticity of the ligand. It is represented by eta. This is represented by the symbol eta n appearing before the symbol of the ligand. When eta is the hapticity of the, n is the hapticity of the ligand. Monoheptoligands, that is eta 1, the organic ligands attached to the metal through only one carbon. Example, methyl group or ethyl group. Diheptoligands, here eta 2, here 2 carbon atoms are attached to the metal atom. Ethylene, example, ethylene group. For example, in the case of Zeize salt, 2 ethylene group is bonded to the metal atom, platinum. Then triheptoligands, that is eta 3, example, allylic radical, allyl group, CH2 double bond CH, single bond CH2, that group is known as allylic group or allylic radical, that is bonded to the metal atom. Here 3 carbon are attached to the central metal atom. And tetraheptoligands, butadiene, here 4 carbon atoms are attached to the central metal atom. So it is known as tetraheptoligands. Then pentaheptoligands, eta 5, it is known as metallocene. Example, metallocene. Example, ferozine is an example. Eta 5, here 5 carbon atoms are attached to the central metal atom. So the hapticity is 5. Hexaheptoligands, eta 6, example, dibenzene chromium, C6H5 twice Cr, the dibenzene chromium. Here the benzene containing 6 carbon atom, all the 6 carbon atoms are attached to the chromium. So it is known as the hapticity of hexaheptoligands. Then the complexes with pi bonded ligands. Example, alkene complexes, alkyne complexes, allyl complexes, diene complexes and cyclopentadienyl complex. The alkene complexes where the alkene group is attached to the central metal atom. Alkyne complexes where alkyne group like alkenyl group is attached to the central metal atom. Allyl group is attached to the central metal atom, means that type of complexes are known as allyl complexes. Then diene group is attached to the central metal atom, they are known as diene complexes. Then cyclopentadienyl complex, example, ferozine. First one, what is transition metal alkene complexes? KPtCl3 eta 2. Eta 2 means hapticity 2. 2 carbon atoms are attached to the central metal atom, platinum. So the name for this one is, according to the IUPAC nomenclature, it is potassium trichloroethene platinate 2. Zeize salt was the first organometallic compound to be isolated in pure form in 1825 by William Zeize. The structure was not confirmed until 1838. Then the discovery spawned a tremendous growth in organometallic chemistry and still serves as the simplest example of transition metal olefin complexation. A Zeize salt has become one of the most cited example of Dworchat-Duncanson model for metal olefin complexation. Here the olefin is attached to the central metal atom and forming a organometallic compound. Then the Zeize salt is a square planar complex with 16 electrons. For example, the pi acid ligand donates electron density into a metal d orbital. The metal donates electron back from the filled d orbital into empty pi star anti-bonding orbital of the ligand. First one is donation from pi orbitals. Pi orbital, that is nothing but ethylene molecule to the metal. Then next figure is back donation from metal to the alkene. So the pi acid ligand donates electron density into a metal d orbital. The metal donates its electron back from the filled d orbital into the empty pi star orbital, that is anti-bonding orbital of the ligand, ethylene. Hence the description pi acid ligand. Both of these effects tend to reduce the CC bond order, leading to an elongated CC distance. The interaction can cause a carbon atom to rehybridize from sp2 towards sp3, which is indicated by the bending of hydrogen atom on the ethylene back away from the metal. See the structure, K plus Cl, Pt Cl3 CH2 CH2, X molecule of water. Here the PtCl3 moiety forms a nearly planar group with the platinum atom. The platinum chlorine bond trans to the ethylene group. The bond distance is 2.340 Armstrong unit, is significantly longer than the cis platinum Cl bonds. That is due to the trans effect. For example, in the cis component, it is of 2.302 and 2.303 Armstrong unit, where if the ethylene group and chlorine are trans, then the value is equal to PtCl value is equal to 2.340 Armstrong unit. The carbon atoms are approximately equidistant from the platinum atom, 2.128 and 2.135 Armstrong unit. The distance from the midpoint of the CC bond to the platinum is 2.022 Armstrong unit. The CC distance in ethylene is 1.375 Armstrong unit, which is slightly longer than the value found in free ethylene. In free ethylene, the value is equal to CC distance is 1.337 Armstrong unit, indicating some d pi b pi backbonding from the platinum atom to ethylene molecule. Backbonding is also indicated by a bending of the 4 hydrogen atom away from the platinum atom. The extent of backbonding may vary according to the substituents of ethylene and other ligands of the metal. For example, in complexes of the type LRHC2F4, where the hydrogen is replaced by fluorine, where L is equal to is acetyl acetone. C2F4 bonds are more strongly and at a shorter distance. RHC bond distance is about 2.01 to 2.2 Armstrong unit than does the unsubstituted ethylene. The rhodium carbon bond distance is 2.07 to 2.19 Armstrong unit. This indicates that the pi acceptor ability of C2F4 is less than that of ethylene, is the most important factor in determining the bond length in this compound. Then we will discuss about transition metal alkyne complexes. The alkynes behave in ways broadly similar to alkenes, but being more electronegative, they tend to encourage back donation and bind more strongly. Chemistry of alkyne complexes reflects some fascinating features. So, for example, in alkynes, the presence of 2 pi bonds at right angles to each other provide a greater possibility for bonding of alkynes with metals. Acetylenes form complexes with the copper 1 or silver 1 metals. Example, acetylene react with the copper 1 chloride in dilute acid to give colorless crystalline complexes of type CuCl2C2H2. The substituents tend to fold back away from the metal by 30 degree to 40 degree in the complex, and the metal carbon distance are slightly shorter than in the corresponding alkene complexes. The disubstituted acetylene also react with butane. 2-butane gives CuCl butene. The structures are like this: the PT pH3 twice, eta 2 pH C triple bond CPH. It is nothing but, what is the organic ligand? Is nothing else, diphenyl acetylene. Diphenyl acetylene. The other one is triphenyl phosphine. So that ligands are attached to the platinum, where the distance of carbon-carbon is 1.32 Armstrong unit. In cobalt complex, CO3 thrice, CO mu eta 2 pH C triple bond C pH CO thrice. Here you get a bridged complex. You get a bridged complex. Then next one, Fe3CO9 eta 2 pH C double bond C pH twice. Here also you get a bridged complex. The alkynes have 2 pi bonding and 2 pi star anti-bonding orbitals, which are quite capable of interacting metal orbitals. Alkynes are more electronegative compared to alkenes. Hence, they are comparatively stronger pi acceptor. The 2 pi bonds in acetylene are placed perpendicular to each other. Hence, these cannot function as a bidentate ligand easily. Only in binuclear complexes, these can be utilized for linking 2 metal atoms by bridging. CO2, CO 6 times C2H2. CO2, CO 8 times plus acetylene gives this compound. CO2, CO 6 times C2H2 plus 2 CO. The alkyne complexes are also formed by platinum and other neighboring elements. The simplest acetylene complexes resemble those of ethylene. Example, bis triphenyl phosphine, diphenyl acetylene platinum. Complexes of the type L2PT RC triple bond CR, where R is phenyl group, L is triphenyl phosphine, may be considered as coordinate complexes of platinum. They have structures in which the acetylene lies almost in the plane of PTL2, forming an approximately square planar complex if each carbon atom in the acetylene molecule is assumed to occupy a coordinate position. The diphenyl acetylene derivative CO2 CO 6 times RC triple bond CR, where R is phenyl group, has been studied by X-ray diffraction. It is found that 2 cobalt atoms are linked to acetylene. The angle between the cobalt atoms and the CC axis of the acetylene is about 90 degrees centigrade. Among the 2 pi bonds available in alkynes, either only one or both may be donated to the metal atom. Reactions of alkynes with the different transition metals species occur in different ways. In the simplest cases, alkynes replace only one 2 electron donor ligand from the original complex. Here only one of the 2 pi electron pairs of alkynes takes part in the reaction. Similar to their alkene analog, example L2PT RC triple bond CR, RPT RC triple bond CR X3, which are similar to that of Zeize salt. Then transition metal Diene complexes. Ferozine is a path breaking discovery of a sandwich compound. The ligands contributing 5 electrons formally upon bonding with the transition metal are called dienyl ligands. For example, cyclopentadienyl group C5H5, ferozine is Fe eta 5 C5H5 twice, bis cyclopentadienyl ion, and other metallocines where metal atoms are sandwiched between 2 cyclopentadienyl rings. Yes, it is remarkable for its stability. The ferozine is more stable It is remarkable for its stability. It is unaffected by air, water, strong bases, and can be heated to 400 degrees centigrade without decomposition. In oxidizing conditions, it can reversibly react with strong acids to form ferrocenium cation FeC5H5 2+. The oxidized Cp2Fe plus ferrocenium cation will repel the electrophile away. Therefore, direct nitration, halogenation and similar reactions cannot be carried out on ferrocene. The formula is Fe eta 5 C5H5 twice. The name according to the IUPAC nomenclature is bis eta 5 cyclopentadienyl ion 2. The ferrocene is a complex consisting of 2 cyclopentadienyl rings bound to a central ion atom. It is an orange colored solid with a camphor-like odor that sublimes above room temperature and is soluble in most organic solvents. The ferrocene is known as sandwich compound. It occurs as highly stable orange crystals with a melting point of 174 degrees centigrade. In solid state at low temperature, the rings are staggered form. The rotational barrier is very small with the free rotation of the rings. Extremely low temperature, that is below 110 degree Kelvin, the cyclopentadienyl rings are ordered and eclipsed. Then what are the different methods of preparation of ferrocene? The Paulson and Keeley synthesized ferrocene using iron 3 chloride and a Grignard reagent and cyclopentadienyl magnesium bromide. The iron 3 chloride is suspended in anhydrous diethyl ether and added to the Grignard reagent. A redox reaction occurs forming the cyclopentadienyl radical and iron 2 ion. The dihydrofulvalene is produced by radical-radical recombination, while the iron 2 reacts with the Grignard reagent to form ferrocene. The reaction is FeCl3 plus cyclopentadienyl magnesium bromide, you get the compound, and Miller and Teboth and Tremaine also prepared from iron and cyclopentadienyl diene, so that it gives this compound. Industrially, ferrocene is synthesized by the reaction of iron 2 ethoxide with cyclopentadiene. The iron 2 ethoxide needed is produced by the electrochemical oxidation of metallic iron in anhydrous ethanol. Since the reaction between iron 2 ethoxide and cyclopentadienyl diene produces ethanol as a byproduct, the ethanol effectively serves as a catalyst for the overall reaction, the net reaction being iron plus cyclopentadiene plus gives hydrogen plus ferrocene. Another reaction is Fe plus 2 molecules of R3NHCl gives FeCl2, iron 2 chloride plus R3N plus hydrogen, the ferrous chloride plus cyclopentadiene plus R3N gives ferrocene plus R3NHCl. Then it undergo acetylation. For example, ferrocene on treatment with acetic anhydride and phosphoric acid and heated about 50 degrees centigrade for about 60 minutes, you can get monoacetyl derivative. The yield is about 90%. When we use acetyl chloride in the presence of AlCl3, you get diacetyl derivative plus the traces of the last compound. Next, the chloromercuration using mercuric acetate, you can get mercuric acetyl ferrocene, and on reaction with lithium chloride you get ferrocene mercury chloride, and on bromination and iodination you can get bromine and iodine derivative. Then Manich reaction in the presence of formaldehyde and dialkyl amine, the presence of sulfuric acid, phosphoric acid, you can get the dialkyl amine derivative. Then lithiation reaction, on treatment with tertiary butyl lithium, you can get lithium derivative, and in the presence of N-butyl lithium, you can also get dilithiated product. Then the structure and bonding of ferrozine. The structure of ferrozine in the solid state as seen by X-ray diffraction is a sandwich structure in which two cyclopentadienyl groups are staggered with respect to one another, whereas electron diffraction study of the vapor shows that in this phase the rings are eclipsed. The ion center in ferrozine is usually assigned to the +2 oxidation state. Each cyclopentadienyl ring is then allocated a single negative charge, bringing the number of pi electrons on each ring to 6 and thus make them aromatic. These 12 electrons, 6 from each ring, are then shared with the metal via covalent bonding. When combined with the 6 d electrons on Fe2+, the complex attains the 18 electron configuration. The reference to ferrous ion, structure of ferrozine is pentagonal antiprismatic. All Cc distance inside the ring are 1.40 Armstrong unit, almost exactly the same as in benzene. Inter-ring distance is 3.22 Armstrong unit and ion carbon distance is 2.04 Armstrong unit, and the compound is diamagnetic in nature. Then the pentagonal ring of cyclopentadienyl group C5H5 is analogous to hexagonal ring of benzene, which is obtained by sp2 hybridization of carbon atom. Then in each carbon, the pz orbital of each carbon atom having 1 electron is used for formation of delocalized pi bond. In this way, 5 electrons from 5 carbon atoms and an additional electron obtained from cyclopentadiene gives a total 6 electrons, which are placed in 3 of the 5 pi bonding orbitals as electron pair, while remaining 2 pi bonding molecular orbitals remain vacant. During combination with the central metal atom, which is D2sp3 hybridized, each cyclopentadienyl coordinates giving 3 electron pairs. The filled orbital T2g orbital of ion 2 form back pi bond with the vacant antibonding orbitals, the pi star molecular orbitals of cyclopentadienyl ion. Thus, each cyclopentadienyl group links as a pi donor and pi acceptor with ion 2. The Mossberg spectroscopy indicates that the ion center in ferrozine should be assigned the +2 oxidation state. Each cyclopentadienyl ring should then be allocated a single negative charge. Thus, ferrozine could be described as ion 2 bis cyclopentadienide, Fe2 plus C5H5 twice. Here, iron is in the +2 oxidation state. The cyclopentadienide is present. C5H5 minus is present, so that iron is in the +2 oxidation state. 2 cyclopentadienyl group is present. So, each cyclopentadienyl ring should then be allocated a single negative charge. Thus, ferrozine could be described as ion 2 bis cyclopentadienide. The number of pi electrons on each ring is then 6, which makes it aromatic according to Huckel's rule. These 12 pi electrons are then shared with the metal via covalent bonding. Since Fe2 plus has 6 d orbitals, 6 electrons, the complex attains 18 electron configuration, which accounts for its stability. In modern notation, this sandwich structure model of the ferrozine molecule is denoted as Fe eta 5 C5 H5 twice. The carbon-carbon bond distance around each 5-membered ring are all 1.4 Armstrong unit, and the FeC bond distance are all 2.04 Armstrong unit. Application: it is used here as fuel additive and also smoke suppressant and chiral catalyst precursor. Ferox gas and diesel fuel additive is a catalyst that is an eco-friendly fuel additive and horsepower booster. It allegedly increase mileage from between 10 and 20% while also significantly reducing harmful emissions. Thank you.